Welcome to the channel NextGen Tech Prep. In today's video, we are diving deep into essential questions and comprehensive answers for the Google Professional Cloud Architect certification. Whether you're preparing for an exam or just looking to sharpen your knowledge, you're in the right place. If you find this content valuable, please hit that subscribe button and ring the notification bell so you never miss an update. Now, let's get started.
You are designing a new insurance claims processing application that will be deployed on Google Kubernetes Engine, GKE. Your company's compliance team requires a complete and non-repudiable audit trail for all administrative actions from day one. Your application must capture who deploys a new container image, who modifies the GKE cluster's configuration, and who interacts with running pods or Kubernetes secrets using kubectl. What should you do? The options are: Option A, enable binary authorization on the GKE cluster, and create a policy that requires all deployed container images to be signed by a trusted attester. Option B, deploy a daemon set to every node in the GKE cluster that runs a logging agent to collect and forward all container logs to cloud logging. Option C, enable GKE audit logging to send Kubernetes API server logs to cloud logging, and ensure cloud audit logs are enabled for the project. Option D, activate the Security Command Center Premium tier to analyze GKE logs and detect threats, vulnerabilities, and misconfigurations in real time.
To arrive at the correct answer, we focus on the keywords Google Kubernetes Engine, GKE, non-repudiable audit trail for all administrative actions, who modifies the GKE cluster's configuration, interacts with running pods or Kubernetes secrets using kubectl.
The correct answer is option C, enable GKE audit logging to send Kubernetes API server logs to cloud logging, and ensure cloud audit logs are enabled for the project.
Why is this correct? C. GKE audit logging captures Kubernetes API server calls, logging all administrative actions, cluster configuration changes, and kubectl interactions with pods and secrets directly to cloud logging for a non-repudiable audit trail. Why are the others incorrect? A. Binary authorization enforces deploy time signature validation for container images, but it does not track or generate audit logs for administrative actions or kubectl interactions. B. Daemon set logging agents collect application standard output and container runtime logs from worker nodes, not Kubernetes API server audit events for administrative commands. D. Security Command Center Premium analyzes security findings and detects threats, but it relies on underlying audit logs rather than enabling Kubernetes API server audit logging itself.
Your product team is building a critical, customer-facing application on Google Cloud. The development team wants to use Spanner for their database to take advantage of its horizontal scalability and low operational overhead. However, the FinOps team is concerned about the direct monthly cost of Spanner and proposed using a self-managed PostgreSQL database on Compute Engine VMs instead. You need to resolve this conflict and ensure the project moves forward with an architecturally sound database choice that balances technical requirements with financial constraints. What should you do? The options are: Option A, provide the development team with a reference architecture for deploying a highly available PostgreSQL cluster on a regional managed instance group, MIG. Option B, suggest using Cloud SQL for PostgreSQL as a compromise to get a managed service at a lower cost than Spanner. Option C, develop a total cost of ownership, TCO, analysis that includes operational overhead, and present it in a workshop to facilitate a decision. Option D, cite the reliability and performance optimization pillars of the Google Cloud well-architected framework to formally justify the use of Spanner.
To arrive at the correct answer, we focus on the keywords Spanner, direct monthly cost, self-managed PostgreSQL database on Compute Engine VMs, resolve this conflict, balances technical requirements with financial constraints.
The correct answer is option C, develop a total cost of ownership, TCO, analysis that includes operational overhead, and present it in a workshop to facilitate a decision.
Why is this correct? C. A total cost of ownership (TCO) analysis evaluates direct infrastructure costs alongside indirect operational overhead. Presenting TCO in a workshop enables development and FinOps teams to collaboratively weigh Spanner against self-managed PostgreSQL, facilitating a data-driven decision that balances technical requirements with financial constraints. Why are the others incorrect? A. Providing a PostgreSQL reference architecture prematurely accepts self-management on compute engine without analyzing total cost of ownership or accounting for ongoing operational overhead. B. Suggesting Cloud SQL prematurely assumes it meets horizontal scalability requirements without resolving the core conflict through a collaborative TCO evaluation. D. Citing framework pillars dismisses FinOps financial concerns without conducting a comprehensive TCO evaluation that incorporates operational labor and overhead costs.
You are deploying a critical application with a stateless, containerized frontend on Cloud Run and a Cloud SQL for PostgreSQL backend. The application experiences unpredictable traffic spikes, and the business requires the ability to immediately roll back a failed deployment to the last known good state. You need to apply a deployment strategy that aligns with Site Reliability Engineering (SRE) principles for both the application code and the database schema updates, while meeting the business's requirements. What should you do? The options are: Option A, package the database schema migration script within the container to be executed on every container startup before the application process begins. Option B, configure the CI/CD pipeline to use the latest container tag for deployments, with database schema changes applied manually as needed. Option C, separate CI/CD pipelines for database schema migrations from application deployments. When deploying a new Cloud Run revision, use gradual traffic split. Option D, use a single CI/CD pipeline that first applies database schema changes and then deploys the new Cloud Run revision.
To arrive at the correct answer, we focus on the keywords Cloud Run, Cloud SQL for PostgreSQL, immediately roll back a failed deployment, Site Reliability Engineering (SRE) principles.
The correct answer is option C, separate CI/CD pipelines for database schema migrations from application deployments. When deploying a new Cloud Run revision, use gradual traffic split.
Why is this correct? C. Decoupling schema migrations from application deployments enables independent versioning and backward compatibility. Using Cloud Run gradual traffic splitting aligns with SRE Canary practices, allowing safe validation and instant traffic rollback to the prior revision if issues arise. Why are the others incorrect? A. Executing migrations on container startup causes race conditions during autoscaling spikes, slows down cold starts, and risks database lock contention across multiple scaling instances. B. Using the latest tag prevents deterministic, immutable deployments and rollbacks. Manual database schema updates violate SRE automation and reliability principles. D. Tightly coupling schema changes with application deployment in one pipeline prevents fast rollbacks if schema modifications break compatibility with the previous application revision.
Your team plans to use Vertex AI to develop and deploy machine learning models for various use cases for fraud detection, product recommendations, and customer churn prediction. You want to enhance the security posture of the Vertex AI and Workbench environment by restricting data exfiltration. What should you do? The options are: Option A, enable private Google access for the VPC network to allow Vertex AI services to access public Google services without traversing the public internet. Option B, enable VPC flow logs to monitor network traffic to and from Vertex AI services and to identify suspicious activity. Option C, create a service perimeter and include ml.googleapis.com and document.googleapis.com as protected services. Option D, create a service perimeter and include aiplatform.googleapis.com and notebooks.googleapis.com as protected services.
To arrive at the correct answer, we focus on the keywords Vertex AI, Workbench, restricting data exfiltration.
The correct answer is option D. Create a service perimeter and include AIPlatform.googleapis.com and notebooks.googleapis.com as protected services.
Why is this correct? D. VPC service controls prevent data exfiltration by defining service perimeters around GCP resources. Vertex AI uses AIPlatform.googleapis.com and Vertex AI Workbench uses notebooks.googleapis.com, so including both in the perimeter effectively secures the environment. Why are the others incorrect? A. Private Google Access allows instances without public IP addresses to reach Google APIs, but it does not establish security perimeters to block data exfiltration. B. VPC flow logs capture network traffic for monitoring and analysis, providing visibility rather than preventive controls against data exfiltration. C. ML.googleapis.com represents legacy AI platform and document.googleapis.com is for document AI, rather than Vertex AI and Workbench APIs.
You have an application that uses Vertex AI Feature Store to manage and serve product features for real-time recommendations. You want to monitor the performance and health of the application. You need to understand the overall duration of a request. What should you do? The options are: Option A, observe the request size in your feature store. Option B, monitor the queries per second for your feature store. Option C, measure the latency of your requests. Option D, track the online serving throughput of your requests.
To arrive at the correct answer, we focus on the keywords: Vertex AI Feature Store, overall duration of a request.
The correct answer is option C, measure the latency of your requests.
Why is this correct? C. Latency directly measures the overall duration or response time taken to process a request, making it the appropriate metric to evaluate request duration. Why are the others incorrect? A. Request size measures payload data volume rather than the duration of a request. B. Queries per second, QPS, measures request frequency over time, not individual request duration. D. Online serving throughput measures total serving rate or data volume per second, not request duration.
A large healthcare provider's primary electronic health record (EHR) application runs on Compute Engine instances with a Cloud SQL for PostgreSQL database, all located in the US West 1 region. A new regulatory mandate requires you to implement and document a Business Continuity Plan (BCP). This plan must ensure that the EHR application can be fully recovered and operational in a different geographical region with a recovery time objective (RTO) of 2 hours and a recovery point objective (RPO) of 15 minutes. You need to design a disaster recovery strategy that meets these strict BCP requirements. What should you do? The options are: Option A, deploy active managed instance groups (MIGs) in both US West 1 and US East 1, fronted by a global external HTTP/S load balancer. For the database, use a cross-region RAID replica in US East 1, and rely on load balancer health checks to automatically fail over all traffic during an outage. Option B, use Terraform to define the application's compute infrastructure. During a disaster, configure the Cloud SQL database in US West 1 to use a cross-region read replica in US East 1, build the environment in US East 1, and promote the replica. Option C, take daily snapshots of the Compute Engine disks and Cloud SQL database. Copy these snapshots to a cloud storage bucket in US East 1. During a disaster, manually restore the virtual machines, VMs, and database from the latest snapshots. Option D, deploy a regional MIG in US West 1 for high availability, and rely on the Google Cloud SLA to ensure the region remains online.
To arrive at the correct answer, we focus on the keywords: Compute Engine, Cloud SQL for PostgreSQL, Recovery Time Objective, RTO, of 2 hours, Recovery Point Objective, RPO, of 15 minutes.
The correct answer is option A, deploy active managed instance groups, MIGs, in both US West 1 and US East 1, fronted by a global external HTTP/S load balancer. For the database, use a cross-region read replica in SEast1, and rely on load balancer health checks to automatically fail over all traffic during an outage.
Why is this correct? A. Active MIGs across two regions behind a global external HTTPS load balancer enable instant traffic failover to satisfy the 2-hour RTO. Cloud SQL cross-region read replicas asynchronously stream data, easily satisfying the 15-minute RPO requirement. Why are the others incorrect? B. Creating a cross-region read replica during an outage is impossible if the primary region is unavailable, causing data loss and violating both RTO and RPO requirements. C. Daily snapshots provide a 24-hour RPO, failing the 15-minute RPO mandate. Manual restoration of VMs and databases is slow and increases downtime. D. A single region MIG provides local high availability but lacks cross-region disaster recovery, leaving the application vulnerable to a complete regional outage.
A financial services company is decommissioning one of its on-premises data centers. As part of this initiative, the company needs to perform a one-time migration of 500 of historical transaction archives to a cloud storage bucket for long-term retention. The data center's internet egress is 1 gigabit per second, which is shared with critical business operations. You must complete the secure data transfer within a 60-day window to meet the decommissioning deadline. What should you do? The options are: Option A, provision a partner interconnect connection with a 10 gigabits per second capacity to accelerate the data transfer, and then use storage transfer service. Option B, write a script that uses the cloud storage CP parallel command to upload the data in chunks over the public internet during off-peak hours. Option C, use storage transfer service to create an agent-based transfer job that moves the data from the on-premises file servers directly to the cloud storage bucket. Option D, order a transfer appliance, copy the data to the appliance using your high-speed local network, and ship it back to Google to upload the data into your cloud storage bucket.
To arrive at the correct answer, we focus on the keywords: one-time migration of 500, cloud storage bucket, internet egress is 1 gigabit per second, which is shared with critical business operations, 60-day window.
The correct answer is option D, order a transfer appliance, copy the data to the appliance using your high-speed local network, and ship it back to Google to upload the data into your cloud storage bucket.
Why is this correct? D. Transfer appliance is designed for offline, one-time bulk data transfers when online transfer over a shared 1 gigabit per second connection would take too long or disrupt business operations, successfully meeting the 60-day deadline. Why are the others incorrect? A. Provisioning a partner interconnect connection for a one-time migration introduces unnecessary lead time, high setup costs, and long-term commitments for a temporary data transfer. B. Uploading 500 terabytes over a shared 1 gigabit per second internet link is impractical because it saturates network bandwidth needed for critical operations and risks missing the strict deadline. C. Storage transfer service relies on the existing internet connection. Transferring 500 terabytes over a shared 1 gigabit per second egress degrades business operations and risks exceeding the 60-day timeframe.
Your company wants to optimize Google Cloud costs for their development and staging environments. These environments are workstations used by developers Monday through Friday, 9 a.m. to 6 p.m. local time. Currently, the environments run on a fleet of NL Standard 4 compute engine instances that operate 24/7, leading to a high monthly cost for resources that are idle more than 70% of the time. You need to implement a solution that significantly reduces the monthly cost of these non-production environments without impacting the development team's productivity during work hours. What should you do? The options are: Option A, schedule the virtual machines to start and stop to match your team's work schedule. Option B, purchase 3-year committed use discounts, CUDs, for the existing NL Standard 4 instances. Option C, upgrade all instances to the N2 machine series. Option D, re-architect the environments to run on a regional managed instance group, MIG, with auto-scaling enabled.
To arrive at the correct answer, we focus on the keywords, optimize Google Cloud costs for their development and staging environments, Monday through Friday, 9 a.m. to 6 p.m., NL standard for compute engine instances that operate 24/7, idle more than 70% of the time.
The correct answer is option A. Schedule the virtual machines to start and stop to match your team's work schedule.
Why is this correct? A. Scheduling instances to start before work hours and stop after work hours eliminates compute costs during idle times, nights and weekends, reducing runtime by over 70% without disrupting productivity. Why are the others incorrect? B. Committed use discounts, CUDs, require a continuous 1-year or 3-year commitment, paying 24/7 regardless of usage, which yields less cost savings than turning off VMs idle greater than 70% of the time. C. Upgrading to N2 instances changes the machine family for performance, but keeping them running 24/7 does not solve the fundamental cost inefficiency of paying for idle resources. D. Autoscaling in a MIG scales based on load metrics like CPU, not developer availability schedules, and adding regional redundancy adds unnecessary complexity and cost for individual developer workstations.
A retail company's most critical application is its online payment processing system. The business has a requirement that the system must be able to survive a complete zonal outage while minimizing cost. You need a design solution that can handle a zonal failure. What should you do? The options are: Option A, deploy the application in an active-active configuration using managed instance groups, MIGs, in 2 different regions, fronted by a global external HTTPS load balancer and backed by a multi-regional database like Spanner. Option B, deploy the application on a regional MIG to provide high availability across multiple zones in the primary region. Option C, configure the regional MIG to use only spot VMs to aggressively minimize operational costs while maintaining high availability. Option D, deploy the application on compute engine instances across multiple regions, and rely on daily snapshots for recovery to achieve the lowest possible cost.
To arrive at the correct answer, we focus on the keywords, survive a complete zonal outage, minimizing cost.
The correct answer is option B. Deploy the application on a regional MIG to provide high availability across multiple zones in the primary region.
Why is this correct? B. A regional managed instance group, MIG, automatically distributes instances across multiple zones within a single region. This ensures high availability to handle a zonal outage while minimizing costs compared to multi-region alternatives. Why are the others incorrect? A. Multi-region active-active deployment with Cloud Spanner is designed for regional outage resiliency and incurs significantly higher costs, exceeding the requirement to minimize cost for zonal failure. C. Spot VMs can be preempted at any time without SLA guarantees, making them unsuitable for a critical payment processing system that requires high availability. D. Daily snapshots serve as a disaster recovery backup mechanism rather than a high availability solution, failing to provide immediate failover during a zonal outage.
Your company is a global financial services provider that processes and analyzes a high volume of credit card transactions in real time for fraud detection. Your analytics team must run complex batch queries on the same transaction data for daily reporting. You need to design a data processing solution that can handle both real-time and batch processing of the transaction data while minimizing operational overhead and infrastructure management. What should you do? The options are: Option A, use Dataprep to ingest the transactions. Option B, use Dataflow to process the streaming data. Option C, use a Dataproc cluster for both the streaming and batch workloads. Option D, use BigQuery for the batch analytics reports. Option E, use Firestore to store and analyze the transaction data.
To arrive at the correct answer, we focus on the keywords, processes and analyzes a high volume of credit card transactions in real time, complex batch queries, minimizing operational overhead and infrastructure management.
The correct answers are Option B, use Dataflow to process the streaming data. And Option D, use BigQuery for the batch analytics reports.
Why is this correct? B. Dataflow provides a serverless, fully managed service designed for high-volume, real-time stream processing, ideal for low-latency fraud detection with minimal operational overhead. D. BigQuery is a serverless, highly scalable data warehouse optimized for running complex batch analytics and daily reporting without infrastructure management. Why are the others incorrect? A. Cloud Data Prep is a visual data preparation tool for visually exploring and cleaning data, not built for high-volume real-time ingestion or processing. C. Dataproc relies on provisioned Hadoop/Spark clusters, requiring manual cluster management and scaling, which increases operational overhead compared to serverless alternatives. E. Firestore is a transactional NoSQL document database designed for application state storage, not for running complex batch analytics queries at scale.
Your company uses a custom-built application running on a compute engine virtual machine, VM. This application processes real-time sales data and writes it to a zonal persistent disk. A recent internal audit requires that you implement a backup and recovery plan to protect against zonal failures. Your company has a strict policy that all backup data must be retained for at least 90 days and stored in a separate project with limited access. You need to implement a fully automated backup solution that meets these requirements with minimal operational overhead. What should you do? The options are: Option A, write a script to create daily backups of the persistent disk. Copy the backups to a different zone and apply a label to each snapshot to indicate the deletion date. Option B, use cloud commands to create snapshots of the persistent disk. Store the snapshots in a regional cloud storage bucket and configure a lifecycle rule to delete objects older than 90 days. Option C, create a snapshot schedule to automatically create persistent disk snapshots and use a script to move and store them in a multi-regional cloud storage bucket. Option D, use the Backup and Disaster Recovery (DR) service to create a backup plan. Configure the backup plan to take daily snapshots and store them in a backup vault with a 90-day retention policy.
To arrive at the correct answer, we focus on the keywords: compute engine virtual machine, VM, zonal persistent disk, protect against zonal failures, retained for at least 90 days, stored in a separate project with limited access, minimal operational overhead.
The correct answer is option D, use the Backup and Disaster Recovery (DR) service to create a backup plan. Configure the backup plan to take daily snapshots and store them in a backup vault with a 90-day retention policy.
Why is this correct? D. Google Cloud Backup and DR service provides centralized, fully automated backup management for compute engine VMs. Backup vaults support isolated cross-project storage with strict access controls and retention policies, satisfying all security and compliance needs with minimal operational overhead. Why are the others incorrect? A. Writing custom scripts creates high operational overhead and ongoing maintenance burden. Additionally, snapshot labels do not enforce automatic deletion after 90 days, nor do they natively secure backups within an isolated separate project. B. Standard persistent disk snapshots cannot be saved directly into cloud storage buckets where GCS lifecycle rules apply. Additionally, using scripted cloud commands introduces operational overhead instead of a fully managed automated solution. C. Persistent disk snapshots cannot be directly moved into cloud storage buckets using scripts. Introducing custom movement scripts increases operational overhead, failing the requirement for a fully automated, low-overhead solution.
Your e-commerce web application includes many products with pictures and videos. You need to improve the application's page load speed and reduce the latency for customer requests. What should you do? Choose 2. The options are: Option A, deploy your application to Cloud Run and enable concurrency. Option B, use Memory Store Tor Redis. Option C, implement CDN with the application's external HTTPS load balancer. Option D, change the database from Bigtable to Spanner. Option E, deploy your application to a GKE Autopilot cluster instead of a regular GKE cluster.
To arrive at the correct answer, we focus on the keywords, pictures and videos, improve the application's page load speed and reduce the latency. Choose 2.
The correct answers are option B, use Memory Store Tor Redis. And option C, implement CDN with the application's external HTTPS load balancer.
Why is this correct? B. Memory Store for Redis acts as an in-memory cache for frequently requested dynamic data and sessions, reducing database query load and accelerating page loading. C. Cloud CDN caches static content such as pictures and videos at edge locations close to users via the external HTTPS load balancer, reducing latency significantly. Why are the others incorrect? A. Cloud Run concurrency manages container request handling and scaling, but does not provide content caching to reduce media delivery latency or database query overhead. D. Switching to Spanner provides relational consistency and global transactions, but does not cache dynamic data or static media assets to improve page loading speed. E. GKE Autopilot manages cluster infrastructure operations, but does not address latency bottlenecks associated with delivering static media or dynamic web queries.
You need to build and deploy a containerized web application to Google Cloud. The application is very write-heavy and requires a relational database as its data store. The application needs to be highly available in multiple cloud regions. You want to minimize operational overhead while following Google recommended practices. What should you do? The options are: option A, deploy the application to GKE clusters in multiple regions and expose the application endpoint with a regional load balancer. Use Cloud SQL as the database. Option B, deploy the application to Cloud Run in multiple regions behind a global HTTPS load balancer. Use Spanner as the database. Option C, deploy the application to a GKE standard cluster behind a global HTTPS load balancer. Use Firestore as the database with multi-region locations enabled. Option D, deploy the application to a GKE standard cluster with a global ingress to expose the application endpoint. Use Bigtable as the database.
To arrive at the correct answer, we focus on the keywords: containerized web application, write-heavy, relational database, highly available in multiple cloud regions, minimize operational overhead.
The correct answer is option B, deploy the application to Cloud Run in multiple regions behind a global HTTPS load balancer. Use Spanner as the database.
Why is this correct? B. Cloud Run minimizes operational overhead for containerized applications deployed across multiple regions behind a global HTTPS load balancer. Cloud Spanner is a fully managed, multi-region relational database that easily handles write-heavy workloads with strong consistency and high availability. Why are the others incorrect? A. Cloud SQL does not support multi-region write-heavy relational workloads natively in an active-active setup. Additionally, managing GKE clusters and regional load balancers across multiple regions incurs significantly higher operational overhead than serverless Cloud Run. C. Firestore is a NoSQL document database, failing the requirement for a relational database. Furthermore, deploying and managing GKE standard clusters creates greater operational overhead compared to serverless Cloud Run. D. Cloud Bigtable is a NoSQL wide column store, not a relational database. Additionally, GKE standard clusters require cluster administration, which increases operational overhead compared to Cloud Run.
Your machine learning (ML) engineers use self-hosted Jupyter notebooks for tasks such as data preparation, model training, and fine-tuning. The operations team then deploys these models in various environments. You want to provide maximum flexibility for ML engineers, promote collaboration with a common toolset, and leverage Google Cloud scalability, while following Google recommended practices. What should you do? The options are: option A, use AutoML for machine learning and Cloud Deploy for model deployment. Option B, use Colab Enterprise for machine learning and DevOps for model deployment. Option C, use Vertex AI for machine learning and machine learning operations, MLOps, for model deployment. Option D, use TensorFlow for machine learning and Cloud Deploy for model deployment.
To arrive at the correct answer, we focus on the keywords: self-hosted Jupyter notebooks, maximum flexibility for ML engineers, promote collaboration with a common toolset, Google recommended practices.
The correct answer is option C. Use Vertex AI for machine learning and machine learning operations, MLOps, for model deployment.
Why is this correct? C. Vertex AI provides managed workbench notebooks, scalable training, and end-to-end MLOps tooling. This offers ML engineers notebook flexibility, seamless collaboration, and scalable model deployment across environments following Google Cloud best practices. Why are the others incorrect? A. AutoML limits custom notebook workflows, reducing flexibility for ML engineers. Additionally, Cloud Deploy is built for continuous delivery of containerized applications to Kubernetes, not managing ML model lifecycles or model deployment. B. Standard DevOps practices lack dedicated ML capabilities like model artifact registries, monitoring, and lineage tracking. A complete MLOps workflow on Vertex AI is required to manage end-to-end model deployment effectively. D. TensorFlow is a software framework rather than a fully managed cloud platform solution, and Cloud Deploy is intended for application software delivery rather than ML model management and serving workflows.
Your employer is a financial services company that recently acquired a popular fintech startup. The startup's core application is a monolithic Python application running on a managed instance group of compute engine virtual machines with a single, large PostgreSQL database. Your development team struggles with slow deployment cycles, and the monolithic design of the startup's core application makes it difficult to integrate new ML-powered fraud detection models. You need a long-term strategy that improves developer agility and positions the company to leverage Google Cloud's advanced data and AI capabilities for future innovations. What should you do? The options are: Option A, deploy the ML fraud detection model to a Vertex AI endpoint. Create a REST API for the model and modify the monolithic Python application to call this endpoint for real-time fraud analysis. Option B, containerize the application, deploy it to Google Kubernetes Engine, GKE, and migrate the PostgreSQL database to Cloud SQL for PostgreSQL. Option C, propose a phased, event-driven migration to a microservices architecture. Use pub/sub for asynchronous communication and deploy the fraud models on Vertex AI endpoints. Option D, migrate the PostgreSQL database to Cloud SQL for PostgreSQL. Replicate the data into BigQuery using DataStream, and then train and deploy the fraud detection models directly within BigQuery using BigQuery ML.
To arrive at the correct answer, we focus on the keywords: monolithic Python application, compute engine virtual machines with a single, large PostgreSQL database, slow deployment cycles, improves developer agility.
The correct answer is option C. Propose a phased, event-driven migration to a microservices architecture. Use pub/sub for asynchronous communication and deploy the fraud models on Vertex AI endpoints.
Why is this correct? C. Decomposing the monolith into a microservices architecture improves long-term developer agility and speeds up deployments. Pub/sub enables asynchronous event-driven integration, and Vertex AI endpoints efficiently host advanced ML fraud detection models. Why are the others incorrect? A. Maintaining the monolithic structure does not address slow deployment cycles or improve long-term developer agility, and synchronous REST calls to Vertex AI retain tight coupling. B. Containerizing the existing monolith onto GKE and migrating to Cloud SQL leaves the monolithic architecture intact, failing to resolve deployment bottlenecks or integrate ML models. D. Replicating database changes to BigQuery for BigQuery ML keeps the monolithic core application unchanged, failing to solve developer agility issues or support event-driven ML integrations.